Welcome, everybody. Good morning, good afternoon, good evening, depending where you're from. I would like to welcome you to this presentation with the topic Dynamic Power Measurement and Accelerated Efficiency Mapping. My name is Alexander Stock. I'm a technologist in the field of electric power test at HBK. I joined HBK in 2019. Before that time, I was a research assistant at the University of Applied Science in Aschaffenburg, and I did a cooperative doctorate with the University of the Federal Armed Forces in Munich. Also, all around the topic measurement of highly dynamic powertrains, machines, measurement equipment, power analysis, all those topics. First of all, I would like to give you a short overview to introduce HBK, who we are. HBK was merged from two companies, Brüel Kjær and HBM, Hottinger Brüel. And both companies are experts in the field of test and measurement and simulation. Brüel Kjær has its expertise in the field of acoustic measurements and simulation, sound, noise, vibration. HBM is a specialist for mechanical and electrical measurements around reliability, durability, propulsion efficiency, electrical properties, and weighing technologies. Most of the analysis on the acoustic side is done in the frequency domain, of course, not only, but most of it, whereas mechanical and electrical calculations, analysis, simulations are done in the time domain, which is the expertise of HBM. And from this perspective, of course, it makes perfectly sense to combine this know-how in one company, HBK, in order to be able to cover the complete measurement chain, including sensors, data acquisition, but also data preparation, evaluation, engineering capabilities, and also simulation. We are the experts in different physical domains. And to sum it up, we can divide it into three major domains: the mechanical one, sound and vibration, and the electrical one. The mechanical one can be divided into a few subdomains like strain, force, load, pressure, torque, and durability. For sound and vibration, it's noise, sound, power, sound quality, and acoustics. And today, within this presentation, we will mainly be in the electrical domain, including subdomains like electrical signals as voltages and currents, but we will also talk about temperature, speed measurement, torque. So depending on the application, you can directly see that these domains, the three main domains, of course, cannot be strictly separated. Depending on the application, they are more interconnected. So we will see that today on the example of a powertrain. Then also sometimes sound and vibration signals are of relevance. And with this short background about HBK, I would like to give you now an introduction to the main content of this presentation. We will start at the beginning with a short overview on the electric powertrain, how it looks like, what are the challenges if we measure in such a powertrain. I will give some information about active power calculation or power calculation in general. We will start with a conventional approach, how this is typically realized. And then I will, based on this, introduce a new dynamic electric power approximation. I will give you measurement examples. We will do kind of comparative measurements, which of course show similarities, but also differences and sometimes benefits of this dynamic approach. This will be, as mentioned, done based on real measurements. And I will at the end show you how you can benefit from dynamic power approximation in order to do, for example, that's just one example, but for example, an accelerated efficiency mapping. I will finish the presentation with a short summary and conclusion. First of all, here you can see the typical topology of an electric powertrain. We have an electric machine, which is connected to an inverter. The inverter on the input side is connected to a power source. So in an electric vehicle application, for example, the power source is the battery. The inverter is used to transfer energy from the battery to the machine, or in generator operation. If we talk about an electric car during electric braking recuperation, we can save energy by transferring it back from the mechanics via the machine over the inverter to the power source, the battery. And now, typically during the development of components, but also of the overall drivetrain, one of the most important optimization criteria is the maximization of efficiency, so the minimization of losses in the system or in the individual component. And in order to assess and evaluate efficiency and losses, of course, we need information about the system. So we need to measure the current status of the system. And relevant quantities to be measured in order to analyze power efficiency and so on are, of course, the electrical voltages and currents between battery and inverter. But of course, also, if we have here a three-phase system, the three-phase voltages and currents, so the AC signals in this context. But of course, as well, the mechanical quantities, which can be measured on the shaft of the machine, torque and speed, for example, using a torque transducer. Also of interest is, especially with regard to doing an efficiency map, is to supervise temperatures in order to make sure that the efficiency map is measured at a constant temperature, but also to supervise if maybe some limit temperatures could be exceeded. So winding temperatures of the machine are a typical example, but of course also temperatures of the power electronics and the battery. And some of our customers also measure vibration signals, which may be caused, for example, by electromagnetic fields in the machine. The electromagnetic fields cause mechanical oscillations leading to vibrations, and at the end, sometimes also to noise. And all these physical quantities should be measured, of course, time synchronously, in order to be able to evaluate further quantities derived from the measurements. Therefore, in this case here in the center of the graphic, over here, you can see a measurement system, the Gen 40B. And this measurement is used for the time synchronous measurement of all these different physical quantities. The setup of such a system can be done, for example, by using a measurement PC connected via Ethernet. This measurement PC could also be used to visualize data, also to do further calculations offline, but you can also do calculations on the system without using a measurement PC. And the calculated and measured data both may be transferred via feed buses, for example, CAN or EtherCAT, to an automation system. And the automation system, of course, can then influence also, for example, the inverter control again. So there are a lot of challenging tasks in order to do a robust and suitable power calculation, efficiency calculation. But first of all, after we've seen now the major topology, I would like to start from the beginning. How to measure voltages and currents in a suitable way if we talk about power calculation. And for this, we can see here on the right side a picture here. It's a bit generic. It's an N-phase system, but if we go back to the application, we have a three-phase machine. Then the number of phases means all conductors which are connected to the system and which are used for energy transfer. So for a three-phase machine, the three phases. Of course, if a neutral conductor would be connected to the start point of the machine, this should also be considered. But of course, CAN communication cable is not does not contribute to the energy transfer of the system. So for a three-phase machine, we have three conductors connected to the system. And for these three conductors, we need to measure voltages and currents. For the currents, the measurement is clear. We just measure the currents in the conductor. But for the voltage measurement, there's a bit higher degree of freedom with regard to the reference potential of the voltage measurement. So in this picture, you can see here floating potential R. This should just mean that it is arbitrary. You can choose what you want. Typical examples in practical applications are, for example, the start point of the machine. It can be the negative DC link potential of the inverter, the neutral conductor, or such an artificial star point, as you can see it over here. And depending on the reference potential, of course, the voltages, the measured voltages may look different, and also the RMS of a measured voltage depends on the reference potential. If you consider a perfectly balanced star point here, like this one in the graphic, which is also what you have here as a hardware, as a measurement hardware tool, then the voltages sum up to 0. And probably a difference between the used reference potential of the measurement and this ideal star point is a so-called zero sequence voltage. The zero sequence voltage has absolutely no influence on the instantaneous and active power, but as mentioned, depending on the reference potential, RMS values could be different, and therefore also apparent and reactive power quantities calculated from those RMS values. And for this reason, in order to do a robust and reproducible power measurement, the zero sequence voltage should always be subtracted in a first step. And this is done in the hardware as well. And it's an important point if we talk about this. It's also the recommendation, for example, in standards like the DIN 4110-2, which also explains that topic in more detail. If you use a Genesis high-speed system, depending on your reference potential on the voltage measurement, you need to choose the corresponding setup, which you have really connected in hardware. And depending on that, in the background, of course, automatically this zero sequence subtraction is done. You can see this here based on two different examples. We have on the left side a measurement against ground, for example. And on the right-hand side, you can see a typical face-to-face measurement, which is also a standard procedure. And depending on how the voltage was measured, in the first step, typically always the natural zero voltages are calculated. So the measured voltages minus the zero sequence component. And yeah, we don't need to look here in the formulas in detail, just to let you know, this is done in the background, depending on your selection of the hardware setup. And this is an important step in order to get comparable RMS values that the results of the RMS voltage and also the reactive and apparent power quantities does not depend on the reference potential of the voltage measurement. In order to compensate this, we need to do these calculations, the subtraction of the zero sequence component first. Now, having measured suitable voltages and currents, we can go a step further to power calculation. For this, I would like to consider again the example of this standard drivetrain topology here, a battery, an inverter, and a machine. In this case, I would like to take a look onto the input quantities here of that machine by means of the three-phase voltages and the three-phase currents. These quantities are measured with the system, and you can see this for an example during steady-state operation here in the left bottom corner. And in a first step, in order to calculate active, reactive, apparent power quantities, RMS values, these are all fundamental period-based calculations. There is an averaging process over the fundamental period, which means in the first step, measured based on the instantaneous measured waveforms, we need to calculate the fundamental period. And this is in our system done by using a cycle detect algorithm. And cycle detect means the cycle is a signal here in the bottom plot, the rectangular waveform here, the purple one. And the length of the cycle is equal to the length of the fundamental period of the measured voltages and currents. And as you can see here directly, since the voltages on the machine input, which is also the inverter output, if we neglect conductor losses in between, these inverter output voltages, they have a high amount of switching frequency harmonics. So this is why they look like this. They are not purely sinusoidal. There's a high content of switching frequency harmonics. Since the machine represents an inductive load, these switching frequency harmonics are strongly damped, so that the currents look more or less sinusoidal. Of course, they still contain switching frequency harmonics, but in a lot smaller amount compared to the voltage. And this is why typically, not always, it's not a must, but typically a phase current is used to detect the fundamental frequency, the fundamental cycle of voltages and currents. This is what you can see here in this picture as an example. So the blue current here is used to do the cycle detect, and the cycle corresponding to that current is the purple waveform. And this is always the first step for power calculation, doing a robust cycle detection. Then with this, we go a step further. We take a look again how power is calculated. In the first step, it's always the instantaneous power. Instantaneous power means the zero sum voltage, so the natural zero voltage without zero sequence component, which we talked about before, is used. It's multiplied per phase with the corresponding current. This is done for all the phases. So in our example, all the 3 phases. And then the total instantaneous power can be calculated by summing up the instantaneous power per phase. This is what you can see here in the top line. And in the second step, the active power as time average of the instantaneous power related to the fundamental period, as mentioned before, can be calculated. So again, the picture from before, we take one of the currents, we detect the fundamental cycle, the purple signal, its length is equal to the fundamental period, and this time length is needed to define the averaging time of the instantaneous power. And if this is done, we get as result the averaged energy transfer per time, which is represented here by the active power. Of course, this cycle-based averaging process is also needed, as mentioned before, for other power quantities, for RMS values, for fundamentals, but also for power factor, efficiency, fundamental phase shift, fundamental waveforms, everything which is based on the fundamental cycle. This is also done in the Genesis system in the ePower suite. You can see here a screenshot of the software tool. We can again find the topology, the standard topology, which I showed on the first slide. We have a power source, we have an inverter, we have a motor. The cycle detection is set up in these blocks. Also, input and output of these blocks can be defined. So the number of phases and how many connectors you want to have to following blocks. And as you can see here, there is also an add component button, which means if you have a more complex system topology, not only one power source, one inverter, one motor, but several motors may be fed by 2 separate inverters, which are on the input side, again connected to one power source. You can build up this flexibly. And all the formulas in the background are generated automatically, and you can visualize the measured sample by sample data, but also the fundamental cycle-based RMS values, power quantities, so all cycle-based results here in these plots here on the right bottom side. To show the process again, this is very open, so you can always see how we do the calculations, which also means if you, depending on your application, for several reasons, maybe would like to do it different, you can put your own formulas below and adapt the procedure by this. But typically, as explained on the slides before, in the first step, we take the measured voltages and currents. Again, please do not look into the details too much right now. It's just to give you an impression that you can always follow our calculations. You can reproduce what we are doing. And for this, I want to show you this slide here. Then we need the cycle detection. Therefore, a few relevant parameters are generated, but the customer does not need to do this on his own. It's set up in the slide we've seen before in the setup sheet, and then these formulas are created automatically. But you can see how it is realized. And in the last step, we do the power calculation. As you can see, the product of the measured voltage and current per phase gives you the instantaneous power. All phase instantaneous powers are summed up to the total instantaneous power, and you can, as a cycle mean, based on the fundamental cycle, on the fundamental period, one can calculate per phase the active power, but also the total active power. This is state of the art. This is the conventional way how a power calculation is realized. And with this, with the background knowledge about the process, we now go to the dynamic electric power calculation. And we start again here with the same topology, same picture. We use the same steady state operating point in this case. Again, the 3 voltages and 3 currents are measured, but instead of using one of the currents as reference to calculate the fundamental cycle, we now use an inverter output voltage in order to detect the switching cycle of the inverter. So the cycle length, which is related to the inverter switching frequency. And depending on the application, this time interval is, of course, much shorter than the fundamental cycle. So if you imagine, for example, 8 kilohertz switching frequency and 50 hertz fundamental frequency, there is a factor in between of 160. And the idea of dynamic electric power approximation is to do the active power calculation based on the inverter switching cycle, so with a much higher increased update rate. And as mentioned, the important information needed from the beginning is the inverter switching cycle instead of the fundamental cycle, which is used for the conventional method. We can have a look on the dynamic power calculation as well. So it's more or less the same calculation procedure, just replacing the length of the fundamental period by the length of the switching period. Of course, one could ask from the beginning, does that make sense? And it can be shown that, of course, it does. It's a method which is applicable for a lot of different pulse width modulation methods, where it makes perfectly sense to calculate the dynamic active power in this way. It provides an approximation of the conventional active power calculation during steady state conditions, just with a much higher update rate, of course, depending on the ratio between switching frequency and fundamental frequency. But it also combines information from the instantaneous power during transient balancing processes with the information from active power during steady state in kind of a new power definition, the dynamic active power. And as said, it's an approximation. So the quality of this approximation becomes better the larger the fundamental period is compared to the switching period, or the opposite way, the higher the switching frequency is compared to the fundamental frequency, respectively. And it can be mathematically proven. This is nothing we want to do here in this presentation, but it can be shown that for the purely theoretical case of an infinitely high switching frequency, and also some side conditions which must be fulfilled with regard to the generation of the pulse width modulation, both definitions are under these restrictions exactly equal. Not always, but for certain restrictions, and for infinitely high switching frequency, this can be mathematically proven. And now, after having introduced the dynamic power approximation, I would like to show you a comparison to the conventional method based on measurement results. And the first one I would like to share with you is a startup process of a permanent magnet synchronous machine. In this case, the startup process was realized without any load torque, without a load machine. So from standstill to a certain constant speed without any load. And now we need again to look back to the process, how power quantities are calculated. As mentioned, first step is in the conventional way, take one of the currents typically and detect the fundamental cycle. So here is, during the startup process, the current of phase 1. Only of phase 1 in order to get a better view. We don't need all 3 currents in this plot because we just use the current of phase 1 to detect the cycle. Here you can see the cycle which is detected based on level crossing, of course, but also some different parameters which must be set up in the setup sheet before. But as you can see, it's very useful, the cycle detect function, to get the fundamental period here of this current. And if we now talk about real-time applications, then it gets clear that all cycle-based parameters can only be calculated if the first cycle has been detected completely. We will go into more detail now. In the bottom plot, you can see the instantaneous power during this startup process. So instantaneous power as product of phase voltage with phase current summed up over all phases. And in yellow, you can see the conventional active power calculation. And in red, you can see the dynamic active power calculation. And based on the fact that in real-time applications, we need the cycle to do active power calculation, this means, okay, one edge here is detected. So now the averaging process can be started. Then all values of instantaneous power are summed up during this time period here until the end of the first cycle is detected. And then we just divide by the number of summed up instantaneous power values in order to get the active power. But this means the result of the active power of this first cycle is first known at the end of the cycle and not before. And this leads to the fact that in real-time applications, we know that value here first time. So what can we do? Of course, we can now go on with the second cycle and show the result from the first cycle here during the second cycle. And this is what is done here in the yellow curve. It's the active power calculated with the conventional power calculation. And by principle, by causality, we can deliver the first result after having detected the first full, complete fundamental cycle. This is by principle the case. Of course, one can imagine that also during startup process, typically, also not always, but typically switching frequency is constant, for example, 8 kilohertz, which means we can calculate the first active power result within 8 kilohertz. So 1 divided by 8 kilohertz, 125 microseconds. So within 125 microseconds, we get the first result of the dynamic active power calculation. And as you can see in red, this is much more dynamic and provides a nice representative dynamic average of instantaneous power. So of course, the instantaneous power also contains all that information, but you cannot see it. But if you use dynamic active power calculation, you get a very nice feeling, a representative average of dynamic active power. So the dynamic information and the update rate of active power is highly increased by doing the switching cycle-based calculation instead of the conventional fundamental cycle-based calculation. Now I want to show you I want to explain again something like back annotation in real-time applications. So as I just mentioned, we have the principal challenge that a value is only known at the end of a cycle. Of course, if you do post-processed analysis, or also a real-time visualization, but with a short delay, you can back annotate your data. This is what is done here. For example, in this case, in the top plot, you can again see in blue the instantaneous power, in red the conventional active power, and in yellow the dynamic active power. Conventional active power based on the fundamental cycle averaging, dynamic active power based on the switching cycle information, and both are representing the average of the blue curve. And then a back annotation is done. Okay, for post-processed or real-time visualizations, including kind of a back annotation, this is possible and nice, as you can see in the top plot. But if you take a look onto real-time without back annotation, which is only possible, or which is the only method you can do if you want to send out real-time information on a field bus to use it for an automation system, for example, then you cannot change the fact that a cycle-based averaging can only be realized after a full cycle has been detected. And with this, you can see that, of course, depending on the application by principle, you have the challenges, which I just explained on the slide before. And if you compare the red curves with back annotation and without, then you see a big difference. Whereas if you take a look onto the two yellow waveforms in the top and bottom plot, the difference is quite small. Of course, there is a difference as well, because the bottom one is also delayed by one switching cycle, but of course, one switching cycle is very short compared to the system dynamic here. So for real-time applications, where you send out active power information on a field bus, maybe to a automation system, there you can have the biggest benefits of dynamic active power calculation. There you get real advantages out of it. I want to show you another measurement example. In this case, the transition between different steady state operating points, which means if you take a look on the left side, we have in the top plot the instantaneous power, and in the bottom plot, the two averaged quantities, the dynamic active power in blue and the conventional active power in red. Since the conventional active power is related to the averaging over the fundamental cycle, during a balancing process, this value changes here stairwise, and each stair length is related to the fundamental period. Again, you can see the big advantage of dynamic averaging. You can see the huge benefit of dynamic active power calculation during this balancing process. You can also see the overshoots, the peaks, which you have in the instantaneous power. You can also see that in the dynamic active power, of course, done in a certain way because we do still averaging, but it gives you a good feeling for the average energy transferred during that balancing process compared to instantaneous power, which is, of course, contains the high frequency content of the inverter output voltage. But what we can also see here is, and that's something I mentioned in the introduction to dynamic active power calculation, it can be shown that it is under some restrictions absolutely equal for infinitely high switching frequency, but the quality of approximation is also high if switching frequency is much higher than fundamental frequency. In this measurement example, it was higher by a factor of 100. And as you can see during steady state, both calculations are very similar. So the dynamic active power provides significantly more dynamic, but also a very precise approximation of the conventional definition during steady state. This is what you can see here again in this graphic. Now, after having shown the differences and also advantages of dynamic calculation with regard to active power, we can see that we can use the same approach to calculate other cycle-based quantities, such as RMS values based on this dynamic switching frequency-based cycle. First one I want to show you is the calculation of fundamental waveforms. In this case, the fundamental voltage waveforms. Therefore, just to keep it always in mind, we have, again, a startup process. The startup process of this permanent magnet synchronous machine. You can see it's the same current which you've seen on the first slide about startup process. This current is used to do the cycle detect, so the red signal over here. And again, of course, we can evaluate the fundamental waveform of the signal, which is based on the fundamental period, the earliest after the first full cycle has been detected, which is here. So in the central plot, you see the inverter output voltage of phase 3, including all harmonics. And in the bottom plot, you can see the fundamental waveform of this inverter output voltage. In red, with the conventional method based on the fundamental cycle. In blue, you can see the dynamic averaging over the switching cycle. And again, you can see, of course, the benefits with regard to dynamic. And here on the right side, you can see the nice correspondence of both waveforms during steady state conditions. What you can also see is that during a startup process, the voltage changes frequency and amplitude continuously. For that reason, it's not a real periodic signal, because periodic signal is equal from period to period. But here, since frequency and amplitude are continuously increased, it's not really periodic. So the Fourier series may deliver some strange steps at the beginning and the end of a period. This is what you can see here, for example, whereas the dynamic approximation does not have this problem. For the dynamic active power calculation, we do that quite simple. You use the inverter output voltage. You just average it over the switching cycle. Depending on the pulse width modulation, a zero sequence component could be included in the voltage. So if you have, for example, a third harmonic injection or flat top modulation, there are zero sequence voltages, but that is not a problem, because on the one hand side, you can see what the inverter does, if it's a special modulation or just a sinusoidal pulse width modulation. And after having averaged all three inverter output voltages over the switching cycle, you can use this averaged quantities and you can calculate a zero sequence component out of it, subtract it from each of the dynamic averaged voltages, and then you get something like a dynamic fundamental waveform. This is the blue curve. So you can calculate a fundamental waveform within the switching cycle as well by averaging over the inverter output voltages over the switching cycle and maybe subtracting a zero sequence voltage component if there is one. Now in the second step, after having calculated dynamic fundamental waveforms of output voltages, for example, you can also calculate space vectors from these fundamentals. And by applying Clark transform, for example, I don't want to go into the details of space vector calculation here. For some of you, it will be a common procedure. Maybe some others of you need to dig into that topic if you are interested in. But I just want to show you that you can use this. And of course, this is a very suitable tool in order to verify and assess the quality of an inverter control. So by using the switching frequency-based averages of the inverter output voltage, you can calculate a space vector out of it. And then as lengths of this complex space vector, since we use the fundamentals, we get something like the fundamental amplitude of a balanced three-phase system within one switching cycle. This is what you can see here as the blue curve. So this is the absolute value, the magnitude of the voltage space vector calculated from the dynamically calculated fundamental voltage waveforms. And you can also visualize the space vector by its trajectory. And in both plots, you can again see the benefit in the dynamic of the switching cycle-based averaging compared to the conventional fundamental cycle-based evaluation. Here, in this case, we have also not a real flat stair. This is related to the fact that fundamental waveforms calculated in the conventional way using a Fourier series are during a startup not balanced, because amplitude and frequency is increased continuously. The voltages are shifted in phase 120 degrees, and for this reason you can get some strange effects here if you calculate the amplitude of such a space vector. And here as well you can see for the dynamic method here the startup process, how the voltage is increased in amplitude continuously, the blue curve, and just the two steps, this one and this one here for the red curve. of course, you can also use these space vectors in order to do further DQ, zero transformation, for example, a park transformation, which can also be used to assess the inverter control, to maybe see if D and Q currents are injected by the inverter in a way that it makes sense depending on your machine topology. So there are a lot of possibilities. And by calculating the length of the space vector, which is the fundamental amplitude of a balanced three-phase system, and which is for sinusoidal quantities a constant, but of course fundamental waveforms are sinusoidal quantities. We have directly the fundamental amplitude of the three-phase system, and this can be used to calculate an RMS value out of it, because for sinusoidal, under sinusoidal conditions, the RMS values can be calculated by just dividing the amplitude by a square root of 2. And for that reason, one can calculate the dynamic RMS value also within a switching cycle. And this is visualized here. So in the top plot, you can see that for the voltages. In the bottom plot, you can see that for RMS currents. The blue line in both plots is always the total RMS calculated in the conventional way, including all harmonics. The yellow line is the conventionally calculated RMS of the fundamental, but still based on the fundamental period. And in red, you can see the dynamic RMS calculated over the inverter switching cycle. And you can see, of course, the same effects as before. The drastically increased dynamic information during a balancing process. Here we have a load step from a higher to a lower torque at a constant speed. And you can still see the equivalence during steady state conditions, left and right to the balancing process. And these dynamic RMS values can also be used to calculate then a dynamic fundamental apparent power. And we started with dynamic active power. Now we have the dynamic apparent power. Therefore, we can calculate dynamic reactive power. And you can see that applying this dynamic calculation method, you can calculate almost all conventional fundamental cycle-based parameters, such as power quantities, power factor, fundamental waveforms, everything. You can also calculate dynamically based on the inverter switching cycle. And with this, I want to close the gap again back to the application in order to show you one nice example where you can benefit from dynamic active power calculation. And this is an accelerated dynamic efficiency mapping. So if we talk about efficiency mapping, the conventional procedure is well known. An automation system is typically used. If it's automized, an automation system is used to define set point values for the inverter control. And typically the automation sends out a trigger to the inverter. The inverter drives to a steady state operating point. After having reached the steady state operating point, the inverter control gives back feedback to the automation system. The automation system can trigger the measurement system. Measurement is done, so data acquisition is started during this steady state operating point for a certain time or a certain number of fundamental periods. Both is possible with our system. And then measurement is stopped. The measurement system gives feedback to the automation system, and the automation system can again give the information to the inverter to drive to the next steady state operating point. And doing this for a lot of different torque speed combinations of interest, the set point value, of course, simplified, only a few points, is visualized here in the top plot. So you can see for one constant speed, sequentially, the torque is increased, but always here for steady state operating points for a certain time. Then after that, the next speed is operated. And again, all the torque values are generated by the inverter control in steady state conditions. So this is at the end a very time consuming process, but of course also necessary to get a very accurate efficiency map at the end. But of course, using the dynamic active power calculation, this could be done in a different way, because steady state conditions, which are necessary for conventional active power calculation, are not needed using the dynamic active power calculation. Therefore, for example, for a constant speed, the torque could be ramped up in a very short time interval from minimum to maximum torque value of interest. And then the next speed is operated. Again, the torque is ramped up from min to max value, and you can save a lot of time by this. What you could also do is, this was just done for reasons of comparability here in this way, but you could also slowly ramp up speed instead of doing this stairwise increase. But this is a detail. At the end, you can see that by using this dynamic method, you can save a lot of time, a significant amount of time. And I want to show you now a measurement which was done with both methods sequentially, not at the same time. On the left side, you can see the result of the conventional efficiency mapping process. The red circle marked the points which were the real steady state operating points measured. And on the right-hand side, you can see the dynamic approach and the result using this dynamic approach. It gets clear that there is a high degree of high level of similarity, but for the right side, it was a drastically reduced measurement time, only at 1/10 of the left side. And I want to show you as well the deviation between those two efficiency maps. You can see that here on this picture. So in the relevant range here, the deviation of both methods is less than 1%, and in most of it, it's even less than 0.5% deviation in calculated efficiency values. But of course, with a drastically reduced measurement time down to 10% of the conventional method time. And so if you need highest accuracy in the efficiency mapping, it should just be recommended to use the conventional method. It's inevitable. If you need highest accuracy, just go for it with this method. But if you, for example, do measurements in end-of-line test, where you just want to do a pass-fail decision, does the machine which is measured fulfill the requirement of 95% efficiency in a certain range, then you could also just go with a dynamic accelerated efficiency mapping. And this could, of course, save you a lot of resources and time, which means if you have fixed time, you can do more measurements. What you could also do is to include the efficiency mapping into a WLTP test, which is, for example, done anyhow. So you can save by this a complete measurement process. You don't need an efficiency mapping measurement and a WLTP test. You can just include the efficiency mapping evaluation in your WLTP measurement. So by this, you can save a complete measurement process. Yeah, this is what I wanted to show you so far as an application example for dynamic active power calculation. Of course, as mentioned before, it's very useful whenever active power or other cycle-based parameters are transferred in real time to automation systems for whatever doing with it then, but just to get the information, the update rate, as high as possible, then this is a very powerful method. And with this, I want to give you now a short summary again. From the beginning, starting from the topology of a typical electric powertrain, we discussed the conventional active power calculation, but we also introduced then the dynamic active power approximation as kind of new power definition, which combines advantages of instantaneous power during transient balancing processes, but also of conventional active power, which is approximated very precisely during steady state conditions if the switching frequency is higher than the fundamental frequency. Higher means maybe a factor of 10 at least to get suitable results, but this is given in a lot of practical applications. We've also seen that this dynamic power calculation approach can be transferred to other cycle-based parameters, such as RMS values, other power quantities, power factor efficiency, and so on. And the dynamic active power can then also be used, for example, to do an accelerated efficiency mapping, where you don't have the steady state requirement in order to save resources, time, and therefore also cost. And you can also do the efficiency mapping as measurement included in your test procedures, which need to be done anyhow, for example, a WLTP test. And it's a very suitable method in all real-time measurements where you feedback information from your measurement system to your automation system and use it for whatever you need. And with this, I would like to thank you. If you are interested in more details around that topic, but also other related topics in the field of measurement on electric drivetrains, please join us on YouTube or LinkedIn. I also put in some references around that topic which we discussed today, but you will find that later on, of course, as well. And now I would like to thank you for your attention. Hope it was an interesting presentation for you, and please contact me also afterwards via email if you have any questions. And now I would like to give back the word to the moderation and hope to answer your questions. Thank you.